So, okay, this is what I just said. Zip phones offer much more functionality, so they are probably susceptible to vulnerabilities. And yes, there are plenty of vulnerabilities out there. You can read bugtrack and everything. So there really is the danger that we have worms that don't exploit vulnerabilities in PCs anymore, but in phones. And I mean, zip phones are really hardware phones that you put on your desk, and then you might have a worm that exploits some vulnerability in some vendor and spreads from phone to phone. And this can happen any day. So we need some way to test these devices. Now, if you want to do this, this is really simple. Zip is an ASCII-based text message protocol. I've said this. It's just like HTTP. It sends ASCII request and response. You can log this with either real. It's not that hard. There are many tools out there. ZipZag is a nice tool. It's a Zip Swiss Army knife. It offers some nice basic features. ZipP is a very nice tool. I believe it's developed by Hewlett Packard, but it's open source. ZipP can read XML files with some scenario and then execute it on a test phone. There's also been a complete testing framework by the University of Oulu in Finland. It's called the Protos Test Suite, where they just used zip invite messages with all different kinds of variations in the headers and sent them to some phones, and many of them crashed and they found some vulnerabilities. And there's actually an RFC about this, because the zip community has realized that their phones are really, or their devices are really complex. So they have put up this RFC where you can find some messages that are standard valid, so regular zip messages that might cause problems, but also a lot of messages that are non-standard conform but might cause a phone to crash, like long header values and stuff like that. So if you're interested and you want to try this out, it's really simple. Think of a test scenario, you write a script using the existing tools, and you execute a test and log the result. And logging the result is really watching your phones if you want to start. So it's not that hard. What we've done, and I will show you this in the next couple of slides, we've written a really simple test tool that uses Netcat and Python, and we've implemented this RFC. So we can now send these messages to any phone we want and log the result. And the tool also has some other tests I will show you in a minute. So first of all, here's an overview. If you want to test a zip implementation, if you want to start, you should probably install a zip proxy like OpenSARE or something like that, because most phones here, this is our phone that we want to test, expect a proxy to be there. I mean, normally you don't need the proxy, you can communicate directly from A to B, but it's much easier if you install a proxy. And then you write some code and send a message to that proxy, which forwards it to this machine under test, and then you can obviously view how this machine reacts, and if it crashes, if it rings, if it doesn't. If you want to try out then if the machine has crashed, you might send another valid message and see if it rings. Of course, you can also do denial of service attacks on a session. Let's assume here we have two phones that have set up a session or are establishing a session. Then you can use a test tool that sends in zip there are messages called buy or cancel on your phone under a test. And if that phone behaves correctly, it should ignore these messages because they're not coming from the originator of the session. In zip, there's what's called a dialog, and it's the combination of the call ID and the tag in the from header and the tag in the to header. There's really some protocol details here, but nevertheless, if any of these values are different, then it's not a message that belongs to the dialog, and the phone should ignore it. Now we've tested this, sending some messages to a phone and see if it reacts and hangs up the call. Of course, if you get more advanced, then you probably will develop a tool here that simulates more than one phone and sends a message to a proxy, which forwards it to the phone under test, and then you send another message, like a buy or cancel message from that, from your tool as well, simulating more than one phone. And of course, you don't need several machines to do this. We've done this with VMware. We use VMware, so you can have your proxy in a virtual machine and your test tool in a virtual machine, and then if you're testing a soft phone, you can install it on the host system, and it works fine. So you don't need like plenty of machines to do this. Okay, so the tool we've developed is called Sisu. Like I've said, it's an implementation of this RFC I mentioned. But it also offers a denial of service test on a session, like I've just shown you, where you send a buy or cancel message to the phone under test after a session has been established or while a session has been established. It also offers denial of service tests on a phone, where it sends 10,000 or 1,000 invite messages to a phone, all different messages. And also it implements, let's say it's a buffer overflow search where you can put long values in chosen headers and then see how the phone reacts. Where the idea is here, if the phone crashes, then there's probably a buffer overflow somewhere, or there might be. Okay, this is what it looks like. It's just, like I've said, it's a Python tool, and there's a menu, and then you can send these messages. You can see here that we've installed it under Linux, but because it's Python, it runs under Windows just as well. So then when the phone crashes, you get these messages here. This is just a soft phone that crashed. You can see this easily. And if you have a hard phone that's somewhere on your network, you probably get this message, and then you see, okay, the phone doesn't react anymore, so it's down. Nothing fancy. So some preliminary results. We're still implementing this tool and enhancing it, but we've chosen 4 phones just to see if it works and check it out. And some of the things we found out, just briefly here. This is a valid invite message from this RFC I mentioned, so it's just a regular zip standard message. And out of the 4 phones that we've chosen for this short test, only phone 1 rings correctly, which is what it should do. Phone 3 crashes, which certainly is not nice. And phone 2 and 4, they don't react at all, even if this is a regular standard conform message. Then if you use a denial of service test where you send 10,000 messages at the same time to a phone, all different messages, 2 phones react correctly, and 2 phones is, well, we put here stressed, which basically means, I should have brought the sound, the phone really rings stressed. You need to listen to the actual sound. It is stressed. It doesn't ring regular. Yeah, it's hard to describe. You need to listen yourself. And then also we did this denial of service test on the session, and the phones we tested really behaved correctly, but we found some other phones where you can successfully tear down a session when you send a message that's not conforming, when you send a message that's really not within the dialog. So there are some header values that are not correct, but the phone really accepts them as if they were in the session. Some other problems I just briefly want to mention because I think they're also important, but I didn't have the time during this talk to mention what's going on. First of all, anonymity, of course, is a problem because zip phones you communicate over the internet, so any intermediary can see who called whom, for how long. The RTP stream can be eavesdropped easily. You can use Wireshark these days and save some packets and then make a WAV file out of it. It's really easy. I skipped this. You can use back-to-back user agents if you want to solve this. Also, emergency calls. We all know that IP networks don't offer quality of service. So if we want to prioritize emergency calls, it's really hard to do. There is some work going on in this area. It's called ECRIT. If you're interested, you can check that out. And also, I think a big problem is or will be usability of phones, because eventually, and most phones have already, the phones have some credentials in them. Let it be your password stored or some certificates. And we all know that HTTP websites where you have an HTTP web connection and you see a certificate, then users already have trouble. I mean, if we all know this. How is this going to work with the phone? You call somebody and the phone displays, well, the certificate of your callee is not valid anymore. What's my grandmother going to do? I don't know. And then actually, how do you display this on these small phones? So I think personally there will also be some issues. Okay. I guess I have another 15 minutes. That's good. Because now I want to come to a different area, and that's kind of the future security for zip. It's peer-to-peer zip. What is peer-to-peer zip? It's basically, it says it right here, it's using a peer-to-peer network for user registration and location lookup. So in the slide I've showed you earlier, you use lots of servers to do this, but you can of course also use a peer-to-peer network, which is kind of nice. Not really what I mean with peer-to-peer zip is ZipShare. ZipShare is a file sharing network that just uses zip as a message format, but it's not internet telephony, it's not user registration, so it's different. And of course Skype doesn't use zip at all, although it is peer-to-peer telephony. Okay, there are some reasons why we want to do this. Of course, we have the usual reasons for peer-to-peer networks. We have better scalability, we have robustness. Yeah, and we probably have some cost reduction because we don't need to take care of our servers. So how does it work? Here again we have the slide I've shown you earlier. Here's regular zip communication. And what you realize here is that all these components that I've circled here are really central components that you need for registration and location lookup with zip. So if we take them out, we might say, well, how does Alice then find Bob? So we can put something else in there, which is called a distributed hash table, which is basically a structured peer-to-peer network that offers some formal guarantees on search requests and stuff like that. I don't have the time to go into detail here, but then again, Bob can join this distributed hash table, Alice can do so, and then Alice can look up Bob's zip URI in this distributed hash table. And on the next slide, I will show you a bit more how this works. Just to give you a rough overview, here we have, again, a distributed hash table, a peer-to-peer network where we have a couple of nodes. Each node has an ID, which is formed by hashing the IP address of the node, and then each node stores some content. Okay, so far so good. And then this distributed hash table offers two primitives, basically just store a key or look up a key. And under that key there is some content. So if Alice and Bob want to use this for internet telephony, what they do is, first of all, Bob joins the distributed hash table with his node. So he hashes his IP address and then joins this distributed hash table. Think of it as just as a peer-to-peer network. Alice does the same thing. She has her IP address and then joins the network. And then Bob, of course, wants to be able to receive calls, so he has to do this register message that he usually sends to his registrar. So here he has his zip URI, and he hashes this to, let's assume it's 206, to find out who is responsible in this peer-to-peer network for his content. So he can then store 206 in the network, and in this case, node 215 is responsible and stores the key, which is the hash of his URI, and the corresponding IP address. So if then Alice wants to call Bob, she can also hash his zip URI and ask to the peer-to-peer network in a message, well, I want to look up 206. So then there's some routing in the overlay, which I don't have time to go into detail here. But eventually, from the overlay, she will get back node 215 is responsible. And she can then contact node 215 because the overlay gave her the IP address. And then node 215 will give her the IP address of Bob, and she can contact Bob. Now, if you're used to think in security, you realize quickly, well, what is about node 215 here? I don't know this node. This is just a node in the peer-to-peer network that stores some content, that stores my IP address, my registration. And of course, if you have a huge peer-to-peer network, this node also changes over time. It might leave the network and the content gets stored at another node. So there are some issues here. Yeah, I put them down here on the slide. First of all, we don't have a central authority, so we don't have trust in other nodes. These are just arbitrary nodes that we have. Then I've said this already, the distributed hash table is usually, or if we think of a real deployment, it'll be highly dynamic, meaning we have lots of churn, nodes leave the network, nodes enter the network, and thus we have some problems here. Also, of course, adversary nodes that are in the network and spoof, they can falsify messages, insert false messages, they can do all kinds of things. So there has been some work on distributed hash table security, mostly focusing on the availability of the whole network. But clearly, if we want internet telephony with zip, we also have to consider attacks on single nodes and single keys, where single zip URIs basically that store their content there. And of course, we have performance issues as well, because we want to initiate a phone call conversation. And also, we want to consider the application protocol. So distributed hash table security is really application specific. And there are some special issues for zip. Yeah, I guess we have some time, so there's just a real quick